Okay, our class already live stream, so let's start again. Good morning, everyone. Uh, wait a minute. Okay, sorry. Wait a minute. Oke, operator Mbak Mbak Fitri, saya belum bisa share screen, Mbak. Oke, udah bisa. Oke, now, okay, there is troubles. Okay, I can share screen now. Okay, let's go to the slide. Okay, can everyone see my screen now?
Yes.
Okay, today we will continue our discussion about the importance of conduction electron in the heat transport in metal. Okay. Uh, so yesterday we show that conduction electron play important role in the electrical transport in metal. So today we will discuss that this conduction electron doesn't only carry electricity, but it also transport heat, and also because of that there are some interesting relation between electric and heat transport, and we will connect that to the thermoelectricity. Okay. So previously we saw that electron, the electric conductivity, electric transport, and the microscopic electric transport can be modeled using a microscopic model called a truth model. So in truth model, we know that the movement of the electron is described by Newton's law, and from that we can connect the momentum and with the velocity and also the current density of the electron. And from that we find that the conductivity sigma depends on n, q square, tau, and m. From this, so there are four quantities that define the conductivity of a system of a metal. N, which is the electron density, tau is the scattering time, and q and m is the charge and mass of electron. So q, the charge of the electron, everybody knows, yeah, charge of the electron is the elementary charge. It's around 1.6 times 10 to the minus to the power of minus 19 coulomb, yeah. And the mass is around 9.1 times 10 to the power of minus 31 kilogram. So there are two other parameters that we need to discuss. Yeah. So there are n, the electron density, and scattering time. So these two will define the conductivity of the system. And previously we studied about the Fermi-Dirac distribution, and that Fermi-Dirac distribution will play an important role. So in the electron density, the electron density will be important, especially in the semiconductor, because in semiconductor there are band gap in the possible states that can be occupied by condensation electron, and the Fermi-Dirac distribution, this F, will change at the zero temperature. F basically only the possible limits the possible energy level to the valence band, but because of finite temperature, in the high temperature, this temperature will increase, and this F will have some tailing in the tailing effect. This the tail of the function will not be zero around at the condensation band, and this means that there is electron density at finite temperature. So, and this is the one that is responsible for the conductivity of semiconductor. And scattering time is defined by this. So we discussed about this. So the scattering time will be quite different for the classical gas and quantum gas. It's a little bit different, and it's related to the drift velocity. So they will all connect the conductivity. So in classical truth model, sigma is just n q square tau per m. But so in quantum, yeah, maybe it will be similar, but there are things that we need to consider, because why? Because in the classic, we consider that the movement of a single electron, but in quantum, we need to consider uh, the effect of the distribution of Fermi-Dirac. Maybe it turns out to be the same, but the specific will, in some limit, the quantum and classic is the same. But to be exact, to be detailed, we need to take into the microscopic version of the Ohm law. In this case, the Ohm law is just Q to N per dot T. Q times this is the current density. Q is the number of is the charge of the electron, and the N per dt is just the number of electron per unit time. So this is the current, and this is the resistance, sigma times A. Sigma is conductivity, and this is the area, and the x is the unit length, and the v is the voltage. So if we want to determine sigma, then we need to manipulate this equation to be sigma equal to 1 over A dx per dt q dn per dv. So this v is the voltage, electric voltage. So here, this is the different point between the classic and quantum, because here now we need to consider n, the effect, the derivative of n to v. So if we change the voltage, how this n will change. This is a little bit different between the classic model, because in classic model we just assume that there is a constant electric field, and here that we want to know that how small distribution, small perturbation, or small change, small effect of V, if we change a little bit of V, how is the electron density will change. So this now can be studied in terms of quantum statistic, because in quantum statistic this n is connected to Fermi-Dirac distribution. The n number of the electron It's depend on just we can calculate that by using the integral of 4 pi v square dv. This is the integral over all v divided by the which is 1 over this is the Fermi-Dirac distribution. So depends on the so how v affect this distribution. V will affect distribution by changing the energy. So in the area with more potential will have different energy when with the electron that doesn't have voltage v. So this v will change, will enter inside this. So if you take a look at this, E minus EV, and it will change to this n. So here QV will enter to this energy. So this is the energy term that is previously only E minus this one, E minus EV. So this E will have some contribution. The Fermi energy will be shifted by the potential energy. And if you take the integration of this integral, then we will have arrive to some proportionality that this n will proportional to the AF minus QV to the power of 3.5. Okay, something like this. So if we take this limit, so if we take this derivation, we can this can be evaluated using this. So if we assume a small v, then this integration will this derivation can be written in this term. Right? And the terms in front of the derivative can be written in this kind of form because the expeditivity is just v, the average tree velocity, the average velocity, and also there are a here, q per a is just n times v tau, so the L. Q is the electron charge and n, so there is a, so it means that this electron density per number of electron per unit area is just the number of electron per unit volume times the length. Length is Vt. So this V come from here. So there are L times V means that's V square tau. So you can take the derivative. Okay, this factor 1/3. What is this? It's just that the V square is the absolute value of velocity, but this the expeditivity is only in one direction. So if you averaging x, so this contribution has x and y and z distribution contribution. So they when they contribute equally because of their random movement, then this can be approached by only the third of the overall square term. And because of that, take we can take this value to be v square and q square tau. And from here we find that this is equal to 9 and q square tau 16m. So if we compare this, we have some, the factor is more or less the same, n v square tau and m. So they still depends on the same thing, maybe, but the detail contribution, the constant here, there are some correction that need to be made. But overall, the Drude model can be still used to describe this the electric conductivity of the material. Okay. Next, we want to study the heat transport. So, how electrons transport heat can be illustrated using this figure. So basically, the transport means that the electron moves from an area that is hot to area that is cold. So it's like if we have in something like this. So if we have if we think of two area, one with more heat energy and one mode with less heat energy, it means that in area with more heat energy, there are more the electron can take like more variative value of velocity compared to the area with cold temperature. And if we connect these two, then the electron will scatter and the system will tend to want to be in equilibrium, and because of that there is transfer transfer of heat energy. And this is what is the principle of the heat transport in solid. And this is because the fluctuation comes from where? It's from the Fermi-Dirac density of distribution of the electron. So in the cold, because of this, in the cold, it's like freezing. They have a constant probability, and here there are the electron can have more electron can have more, I mean, more large velocity and large energy, and then they have more heat energy. So now thermal conductivity is defined by the rate of the movement of the heat. So the Q per dt equal K, which is the heat, the conductivity, thermal conductivity. A is the area, and dt per dx is the gradient of the temperature. So this is the image. So if we have hot part and small part, so the mean path of the electron is a little bit different. In a cold area, electron tends not to move a lot, but in the hot area, this electron tends to move a lot, and this means that the electron wants this electron move more, and they want to go to the other side. So now we can manipulate this equation again, like in the electric conductivity. We find that this K kappa is 1 over A, the x per dt, dq per dt equal to this V L 3V. So this is V, the average velocity, divided by 3, because this is the x per dt, it's just that, and L per V is just the A is V divided by L, and the Q per dt is N, say this is the heat capacity, the Q per dt. So the change of heat uh, because of temperature difference, heat capacity. Okay, now we connect L to the V, like as previously. L is V times tau. So now there is V square, 3 tau, and CV. And here now this CV is quite different if we discuss classical gas or a quantum gas. So in classical gas, CV is just 3 divided by 2 kb, and P square is just the average in the Maxwell distribution function, Maxwell kinetic theory. We discussed yesterday that the day before yesterday, that V square is just 8 kbt divided by pi m. So now kappa, we can, from this we can find that kappa is 4, and n is the density here, and electron density, times tau kb square t divided by pi m. In the quantum Fermi gas, this is the CV discussed in the free electron model, the condensing electron model. Now this is depends on T, the temperature, but the V square, the average velocity, doesn't depend on T. It depends on the 9 EF 8m. So it only depends on the Fermi energy because of this distribution, Fermi-Dirac distribution. So this is the main difference between these two models, classical gas and the quantum quantum gas. Because in the classical gas, the one that depends on T is the average velocity, but the CV is more or less constant. Differently, in the quantum gas, the CV is the heat capacity depends on T, so it is 0 at 0 temperature. For the V, the velocity is quite constant. So the actual figure here that we show is actually it's more or less this part, I think, because the V is more large here. So this is the illustration is quite correct for this, not this one. Okay, but overall, if we take the value of the heat of the thermal conductivity, the kappa, both of the kappa depends on T. So more or less the conclusion, I mean, in terms of thermal conductivity, this K is depends on, like, more or less the same physical quantity, that is n, the electron density, tau, the scattering time, collision time, and T is the temperature, M, or the mass. They have the same. So the main the one difference is only the constant. This is 4 divided by pi. So 4 divided by around 3 point something. So it's on the order of 1 something, 1 point something. And this one is 3 pi pi square divided by 16. So 3 pi square is equal almost pi square is 9 something 30. So it's around 2. So this the heat capacity of the quantum Fermi gas is a little bit 2 times this one. And that comes from this decoration of the CV. I think. So more or less is they have the same value. So which one is correct? And now we come to a interesting relation. So this electric and heat transport, if you notice, they have a quite a similar uh, principle. Yeah, they basically comes from the statistic of the movement of the electron and have similar formula. Yeah. The one the heat as this the n per dt, something like this, and their dependency is quite similar. So this sigma, the electric conductivity, depends on the velocity, average velocity, and also to tau. And it's also the same for the kappa. Kappa also depends the square and tau. So this little nice coincidence have some interesting phenomena. It's interesting phenomena. So what do you think the interesting phenomena is? So what do you think the relationship between electric and heat transport? Okay. Hello everyone. So what do you think about this similarity? What does this imply?
They have same scattering time, is it?
Same what?
Scattering time tau.
Yes, scattering time. Yeah, I mean, yeah, that's the for what the formula said. But what's the implication? If their proportionality is the same, what does mean? What does that mean? So they behave
They
like
are directly proportional between the electric
yes, yeah,
conductivity and heat conductivity.
yes. I want to hear that. That's good answer. So they are directly proportional. It means it's a natural phenomena that we observe every day. That is, a good electric conductor is also a good heat conductor. That's the conclusion that is reached by this theory, by this model. That is the uh, good electric conductor is a good heat conductor. It can be shown if in the classical ideal gas or quantum Fermi gas, they both have the same conclusion. Kappa is depends on this and kappa depends on that. If we take a look at the ratio, kappa divided by sigma, it depends on T. It's proportional to T. It's kappa and sigma proportional to T. So the difference between classical ideal gas and quantum Fermi gas is just this proportionality constant, but overall it has the same ratio. So if you measure the heat conductivity and the electric conductivity of a material, then you find that those ratio tends to be higher when the temperature is higher, getting higher and getting higher. And it's often called Wiedemann-Franz law in physics. It's called Wiedemann-Franz law. So recent research, uh, so this area of physics is also researched as a thermoelectric law or something. So many people still actively research about what kind of material that uh, doesn't obey the Wiedemann-Franz law. Why? Because sometimes we want to, if you have computer, for example, of your computer, you want a good computer that is can be manipulated easily, is fast and doesn't get hot very fast. That is, if you buy a laptop, usually like thinking of is it can it perform well at high like high computation. If you want to compute many things, or you use for drawing or for graphic modeling or something like data analyzing, your computer gets too hot, very tends to get very hot very quickly. And why? Because yeah, this is almost all the materials obey this Wiedemann Franz law, and that's why if you have many electric and if many like voltage different, and if you have many electric current, then of course you will conduct also many heat. Will your laptop will receive many heat and it will conduct many heat, and the circuit will get hot very fast. And the current research, they want to make a faster computer without getting the unnecessary heat. So because of that, uh, the people now, many people research about materials that doesn't obey the Wiedemann Franz law. So they want materials that with have small kappa, so conduct thermal or conduct heat very poorly, but conduct electric very effectively, or opposite, something like that. Okay, so those relation of the electric transport and heat transport, they are also sometimes interchangeably. So they don't voltage not only yeah, in most of the material, voltage influence on the electric current, and thermal gradient only only influence heat current. However, in thermoelectric materials, so when we move electron, we are not only moving the electric charge, but we also move the energy because of this statistical thing, statistical the microscopic movement of the electrons. We not only carrying electric current, we also carry the energy, and energy that means the heat current. So in most of the metal, or most of any solid state, any solid metals, if we talk about the electric current, there will be also a heat current moving. That's the consequence of the previously Wiedemann Franz law. So they have this conclusion, and that means that in most of the area, most of the phenomena, electric current doesn't occur independently. So there are other things that follows. The most important thing is the heat. So the transport will also follow electric transport, and it's called the thermoelectric effect, thermoelectricity. And this is not that so even though it's undesirable in laptop or in any electric appliance in your home, however, it has some usage. So there are two kind of uses that I want to introduce to you. But we won't go any deeply, it's just some introduction. So there are thermoelectric power generator, in which we have we have two materials that have a different temperature. We have a material, so a material with different temperature, and those different temperatures will make the electron move to the other direction, and we can use that as a electric uh, source. So if we utilize that, then if we make that a closed circuit, then we can make a power output, something like this. And more in physics, the important effect that describe the thermoelectric power generator is called Seebeck effect. Seebeck effect is the electric voltage, the generation of electric voltage using a thermal gradient. And usually, it's not implemented by only using one material, but usually implemented using two materials. So in one material, the one that moving is the electron, and in the other material, the one that moving is positively charged. What is this? It is a hole. It's called a hole. So the absence of electron. But the different discussion, maybe uh, in later lecture we will learn about this or not. So here the electron will move, and because of this positive charge, so we can have some electric current moving. And this circuit is also often called thermocouple. It's only two because of the coupling, so it's called thermocouple. Or it can be make you can make a series or parallel uh, circuit about that, and it's also called thermopile, something like that. And it's so the more So you can get more voltage difference, if you use more thermoelectric material. And also not only for thermoelectric power, we also have what is called thermoelectric refrigerator. So this is oppositely, by using electric current we can move heat. So it's called in your lab maybe you will have something like this. So it's called Peltier device, and it's based on important effect. It's called Peltier effect, if found by Peltier. So Peltier effect is you can use a DC power source, electric power source, to move the heat in your desirable direction. So it can be used for refrigerator. So if you absorb heat from this area, that means you are cooling this area. So from this point of view, it is a refrigerator. But in the other side, you can throw heat there. I mean, you can also make like thermoelectric cooking, something like that. So you can move heat from one place to the other, and it is usually used in lab, in small lab, because like in small area it's like in lab it is undesirable to use fire. And instead of fire, if you want to give yeah, fire maybe usually used like in chemical lab, but in physical lab maybe it's a little bit dangerous. So especially if you study like semiconductor or something, like small area, uh, small sources. So in that case, usually we use a Peltier device. This Peltier, and in this Peltier, you can make a hotter area or a colder area by using this electric current. And this is quite an interesting effect, and is still uh, studied widely in the scientific community. Okay, so that's all about the electric, the transport to the conduction electron. Okay, before we move to the next topic, do you have any question? Do you have any question? Okay, please tell me if I go too fast or okay. If it's clear, then we can move to the next one. It's heat specific of solid. So why we study heat specific of solid? So because it has some relationship with the heat transport, and we will study the high temperature limit and low temperature limit, and also we will describe interesting model by Einstein. Yeah, maybe you all doesn't do not expect did not expect that Einstein make contribution in this area, but like in Einstein is quite a theoretical physics that study quite a wide area of physics. Yeah. Not only like in special relativity, they also contribute to some quantum mechanics, and also in this transport area in solid. So if it is your first time hearing about Einstein contribution to solid state physics, then I hope I can make you more interested in this area of research. Okay, first of all, why we study the heat specific? Yeah? Because previously it is I have shown you that it's related to the heat transport. Okay, so heat transport is divided by three. As you all know, there are convection, radiation, and conduction. It, especially there are gas. If you recall, there are three basic state of the matter: gas, liquid, and solid. Can you tell which one uh, carried by convection, which one carrying radiation, which one is carrying conduction? Can you tell me? Any one of you? Hello?
I guess for conduction is for solid, right? And
Yes.
convection is for gas and liquid. And radiation is through any matter it can radiate. It can like penetrates any matter. It can
Okay.
like gas, liquid, or solid. It can penetrate depend on the strength of the radiation.
Okay. Is there any other opinion? Okay. Any other opinion? Okay, basically it is, yeah, you are correct, because conduction mainly occur at solid, and convection mainly occur at liquid and gas. But yeah, liquid can have some conduction, yeah, but it's really smaller than this, and it's convection. But radiation doesn't need medium. Radiation doesn't need medium. It's directly the transfer uh, of energy of heat through the photon, through electromagnetic radiation. So that, as you remember, that electromagnetic radiation doesn't need any medium. In a vacuum, it can radiate, so it carry this radiation. Yeah, in material, it really depends on the material. Some materials can be radiated, some is not. Some absorb radiation too effectively, so that there is no conduction. So in our discussion, if it means heat transport, it generally is a conduction, because we are talking about solid. Uh, but however, in as we saw in the previously, that the conduction of heat in the solid is is conveyed by electron, and this electron can be modeled as a gas. So maybe microscopically, it all doesn't really uh, it's all like basically the same kind of effect. If you take a look at the microscopy, it's just in convection, what's moved is the whole atom, proton and electron all moving together. However, in the conduction electron, the one that moves is mainly the electron. So that's the main difference of the conduction and convection. However, today we saw uh, that not only electron contribute to the conduction. Okay, conduction electron, we transferred by electron, as we mentioned earlier, that it comes from the movement of the electron, and it can be described by using classical gas or quantum Fermi, or quantum Fermi gas. Now, as I mentioned, this convection has contribution to electron and proton, so they move together as an atom, a free atom. However, in conduction electron moves more freely than photon. So what come in mind is really only does only the conduction electron contribute to the conduction? Does electron contribute to the conduction, or the proton? Can the proton contribute? The answer is yes. The transport also carried by the proton. Because if you look at the bottom animation, the heat can be transferred not only by electron but by proton. So this, for example, if you have the nucleus, the proton, even if the proton doesn't move really really fast, it doesn't really move anywhere, but they vibrate. We call this the proton. When in a solid, proton is placed really periodically. It's called lattice, usually called as a lattice. So even though that in compared to electron, it doesn't really move at all, because the mass is quite different. The mass of the proton is thousand times larger than electron, but overall they still have that kind of collective vibration, and this vibration will be responsible for the reproduction. Okay, what kind of, so now we will study the heat specific of solid in light of not only the electron but the contribution from the lattice, from the proton. So this is the experiment data of some materials: lead, aluminum, silicon, diamond. It's all solid, and this is the value of their heat capacity. This is monatomic solid. I mean, solid that pure, like a one element solid. They have this kind of behavior, and there are some. There are high temperature limits. So if you see here that as the temperature become larger, they approach value here, that is 3K or sometimes 3R. That depends on how you define this heat capacity. So they become more or less a constant value at last temperature. So this high temperature limit can be explained in terms of equipartition principle. This principle in statistics is observed in in molecules, free molecules. Molecules in high temperatures obey this. For example, in the gas, yeah, especially in the gas. So if I have here hydrogen atom H2, so the H2 the hydrogen molecule in the gas of hydrogen molecule has three kinds of heat capacity. Has three value of heat capacity depend on the temperatures. In low temperatures, so the heat capacity is 3 divided by 2. Yeah, usually R, I get it kb. And in the medium temperature at room temperature around 300, they are 5 over 2. And in the very last temperature, they are 7 over 2. So what does this 3 per 2, 5 per 2, what does this value means? Yeah, it means some kind of deep physical meaning here. So it means that molecules have the same average energy associated with each independent degree of freedom. It's called equipartition principle. So each partition of energy has a equivalent contribution. So there are one half of kT or half of RT per molecule or per mole. This is the Boltzmann constant. It's gas constant. So each of the energy has 1/1 half kT. What does this mean? This means, for example, for at low energy, the H2 atom, H2 molecule only move. They don't really vibrate. They only have translational movement. So they only move like in the X direction, Y direction, and Z direction. So there are three kinetic energy. There are three degree of freedom in their energy. The three contribution of kinetic energy has three contribution due to the X movement, Y movement, and Z movement. And because of that, these three, each of them has half kT. And since Cv is the derivative of the energy over temperature, that means it's just 3 over 2. So the overall energy is 3.5, 3 divided by 2 kT, 3 kT divided by 2, okay, because of that is 3 over 2. And at room temperature, this hydrogen atom has some additional energy, not only the translational, but it can rotate. So like your like your mobile phone, you can rotate this direction and the other direction, something like that. So it can move in two directions, in this XY plane and YZ plane, XY and YZ plane, not in this direction. So if you think of a dumbbell, you can rotate here and there, but you don't rotate this direction because yeah, as you remember, the electron is just a cloud of electrons. So if rotated doesn't mean anything. So only two rotation uh, is dominant and two rotation have meaning. So this is just R square and L is 2. So there are two energy. Each of the energy contributes to another half kT. That means total is 5 now. So there are change kT here because of this. Contribution becomes dominant here. So if they become larger in this temperature, so they contribute to the Cv. And lastly, in the more higher temperature, there are vibration. So this H2 can have vibration in this direction. This direction they can have vibration, and because of that, the other additional kT in the direction. So this two is associated with the kinetic and potential energy of the system of the vibration. So this is the contribution of vibration. Yeah, one conclusion is that vibration of the materials, vibration of the molecules contribute to like 2 times half kT. So the contribution is kT. That's one conclusion that we can conclude. This is in gas. So this is a nice. This is called equipartition principle, and we can utilize that for describing the lattice vibration of in sorry So in solid, we don't have really translational movement. So microscopically, they are bounded. Yeah, they are bounded in the lattice. lattice. So the one that's so you don't have this. You don't have translational energy. You don't have rotation energy. You only have vibration. Vibration is contributes to kT, right? Because of that, there are three kind of energy. Yeah? Because of this, if gas you only have this direction, but in the lattice you have three kind of vibration. In this x direction, y direction of x, y direction, or z direction. There are three. So each of them has a half kt, half kt, half kt, half kt, half kt. So there are six times half kt. So that means 3 kt. And 3 kt means the Cv becomes 3k or 3R, something like that. So this is what happened here. So for solid, for lithium, potassium, if you see it, lithium, sodium, potassium, something like this, Mg, magnesium, something like that. All of the solid, this black one is solid. Yeah. In solid, usually so have Cv around 3R, 3k, something like that. But for gas, like iodine, chlorine, they have larger. For this is 7.2, like three and a half, or three and a half, or two and a half, or three and a half. There are nine and a half. There are four. Three and a half. There are four. In H2 you have this is seven and three and a half. And this because of increasing degree of freedom, because it is a gas. There are increasing high degree of freedom, and because of that, it has many CV larger than 3R. Yeah, but overall for solid, the black one, we have 3R, and this is called Tulong Petit law. So it's called Tulong Petit law. So these two people study this, and they observe this tendency through the solid. Okay. Now, interesting thing is that this KB, the Dulong Petit law, only show at high temperature. We want to know why. Why is that happening? So we will see at the low temperature, and low temperature become zero, right? So we need to think why why is that happening? So in classical vibration, they should have a constant value, but in quantum, we need, we need to take it is a vibration oscillation. So have all of you study quantum physics? How many among you study quantum physics? How many among you already study quantum physics, quantum mechanics?
Sorry. Quantum.
Most of us has.
Oh, okay,
I
you
think
take.
most of us.
Okay, okay, good. So do you understand? Do you remember about the quantum oscillation, quantum oscillator harmonic? You remember?
Yes.
Okay. So what is the energy?
Uh, it's NK pi over. I just quite forgot about the formula.
Okay. So is it continuous or is it discrete?
So I
Anyway.
think it's like for harmonic oscillator. It's like a parabolic curve, right? Continuous.
Okay, okay, yeah. I think yeah. Please try to remember. Yeah, at least the energy now is not it's not the same as classic. Yeah, that's one thing that we need to understand. Okay, anyway, and please everyone fill the attendance. I already give the attendance link in the chat, so please see it. So yeah, we need to remember, in quantum physics, oscillation is quite it's among the first thing, like the first or earlier things that you study. I mean, in the so What kind of textbook do you use for quantum physics? Sorry, you study quantum mechanics?
For me, I think most of us using the Griffith one, Griffith
Okay,
textbook. Yeah.
So do you remember the like h bar, omega, and n plus n plus half? Okay, it's got it. At least so the if we're talking about the quantum oscillation, then we have some quantized energy, because quantum is quantized energy, and the movement of the electron, movement of the vibration, any vibration has, it must take uh, like discrete numbers, some possible value. So it cannot has all the value, but it has some value. So this vibration is what is measured as temperature. So we will now like try to implement this quantum oscillation into our calculation for heat specific. So what is this graph? This graph is just an illustration of how the uh, energy of vibration, energy of particle vibration depends on the distance between two atoms, for example. This, so if you have like hydrogen atom, for example, hydrogen molecule H2, so we can write it something like this, and the distance, the energy of the oscillation really depends on the energy of the distance of between two. So in classically you have this red curve. So you have some like optimum energy, minimum energy here, and uh, usually the oscillation tends to occur between them. So in the molecule, they are the most like stable energy, and if you have higher energy, it can do something like that. Okay, but it can take any energy. It depends on the temperature, something like that. Okay, this is the red one is the classical picture. Classical picture. So it has the energy only depends on the distance, like that. However, in a quantum, not all the energy is possible. Not all the energy can be occupied. So there are some forbidden area. Yeah, that's the typical of the typical of quantum mechanics. So there are forbidden area, and there are forbidden energy, and there are energy that can be occupied. So this is called the energy level. Yeah. So the energy now is quantized. So it's around something like that. So now that's the even though our discussion is mostly about classic, in ideal gas we study about the classic, but we already saw previously in the constant electron we need to study the quantum property of electron to be able to understand the movement of the electron correctly. That's why here, if we study the heat specific of solid as a whole, if we want to study the contribution of the proton of the lattice, we also need to take account to this oscillation as a quantum effect. As a quantum effect. So that's what Einstein, the contribution of Einstein comes into play. So Einstein has proposed a kind of solid. It's called often called Einstein solid. So they have some kind of spring. It's uh, atoms or the protons inside the solid behaves uh, as a mass with connected with many spring. So they are connected periodically by the spring, and the spring generates energy. So generates oscillation, and the energy of the oscillation depends on the how much is like the spring constant and the mass of the electron. Now this energy has the spectrum of energy, and it can be, so what's Einstein model do? Einstein model approach this kind of like energy, yeah, and this energy level, it approach it as a quantum oscillator harmonic, which is studied in your textbook, in Griffith or in any. So they use this is among the first, like the first model, the first simple model that is used in the textbook. So we have potential energy in the form like a simple spring, sorry, it's half over kx square. K is the spring constant. So now you remember about this? Do any of you remember? So if you have a spring, a mass connected to spring, the potential energy, the classical potential energy is half kx square. If you input it in the quantum mechanics in the Schrodinger equation, you find that the energy is quantized. The lowest energy is not zero, but it's half over h bar omega. This is omega is the characteristic frequency, the angular frequency. So, okay, do you remember it? Does anyone?
Yeah, I just read.
Yeah, does anyone forget about this already? Okay.
Yeah, I forget a little bit actually.
Okay. Okay, this is the main assumption of Einstein. So Einstein used this assumption to explain the heat capacity of solid. So now the energy level is quantized, and now we can find the oscillation energy. So what this means? So this energy that's usually like depends that doesn't really exactly as parabolic energy, but it can be approached, it can be approximated using a harmonic energy, and using that we will we can calculate the oscillation energy, and it's called, this is statistical physics. Yeah. So if we want to know the energy, we take an average of all the possible energy, and we assume a probability. This probability is classical probability. It's exponential minus b a n. What does this mean? This means that there are possible energy. Yeah, there are energy. This energy is, so harmonic oscillation, quantum harmonic oscillation has possible energy, and there are forbidden energy. So we only take account the possible energy. It's n, all possible n. So from n 0, 1, 2, 3, 4, 6, 5, 6 until infinite. So the energy is h bar omega n plus half. So we take this all possible n, but we take a weighted average. So we don't assume that, we assume that each energy level has different probability. So with more higher energy, of course, is have less probability. So this energy vibration tends to want to occupy like more less energy have more probability. It's like in the Maxwell, in the gas ideal, something like that, something like Fermi-Dirac, and something like that. So in classically this is the case. So any energy with lower state usually has more probability. Now, so we can this probability is proportional to the exponential minus theta en. So by using this, now we can calculate that by sigma n from 1 to 1 or 0, yes, sorry, for 0, sorry, 0 until infinity, that we can find this is from 0, sorry. And if you take a little bit of mathematic manipulation, you can find here that en is just, we can take the we can take this from here, the differentiation of delta b, and because of that it's become, so if you take uh, this right side is exactly the same as this left side, so these two is exactly the same. So we can simplify the calculation by only calculating this right side, none of this one. So these terms inside sigma, the terms in below, it's called the partition function. You can calculate it by using n. So all possible n, I input all possible n, it should be from 0 here. So it's can calculate it and show that this is proportional to exponential. Beta h bar omega 2, and beta, and this one is divided by exponential. Beta h bar omega minus 1 is equal to the 1 over, if you have some little bit manipulation, is 1 over sin h the hyperbolic sinus function of beta h bar omega divided by 2. Beta is kBT, something like this. And now we can find the heat capacity Cv by taking this, inserting back here, and by taking derivation of u to t, you can find this messy formula. Even though it's messy, but I can show you that this now describe this can be used to describe the heat capacity quite nicely. So we discussed the one dimension. So for two dimension, we just take there are x, y, z, so there are 3 times. So if we plot this the Cv, exactly like before, the exact formula, take this formula and times 3, because of there are 3 contribution, and we can plot it something like this. This can be plotted to be function something like this. So you can see the resemblance here. So now using Einstein solid is the model of heat capacity in solid, we can show that there are some limiting, there are some trend that can describe the heat capacity. So at high temperature, the capacity become as predicted as the classical, so it's become 3K. But at zero temperature, the Cv becomes 0. So this is again so that the behavior of the of proton of lattice inside the solid is cannot be explained by classical physics only, but we need to consider what's happening inside microscopically. So in microscopic level, the quantum physics play important role, and because of that, this kind of behavior so, and there are some transition from 0 to 3K here. Do you have any question? So I hope now you are interested that okay, Einstein contributes to many things, yeah? And there are some theoretical aspect of physics that happening inside a material, inside a solid material, a solid state physics. Okay. And that's discussion about the specific of solid. Okay, before moving to the next one, I will show you that yeah, this trend, yeah, this Einstein model can describe some of the trend. However, we need to take more full quantum. So this is my last slide and my last discussion about this topic, the heat and the transport in solid. Yeah. So we will discuss the heat transport, and we will have more full quantum description about what's happening. So let's now focus on the collective lattice oscillation. And this collective lattice oscillation, of course, it cannot be treated like little bit. So we discuss about this. So this lattice oscillation is not so this instant solid is not a full quantum description of what's happening in solid. It's a somehow implement quantum energy, but we need to discuss it more. So what is lattice oscillation? This is the one that I didn't show you yet. So lattice oscillation is very important in solid. So it can carry many things, even though each of the, if you look at this picture, yeah, each of the proton, each of the nucleus or the valence, each of the atom, or the valence atom here, atom doesn't really move anywhere. It's just moving right to left, up and down only. But you can see that it can carry something. Yes, you can see that there are something carried here. So this is the principle of oscillation, and this collective oscillation play important role in this. And it's usually called phonon. Why does it called phonon? Do you have any idea? Does any of you have any idea why the lattice collective lattice phenomenon is called phonon?
Because it's like a particle, like it's a particle of sound.
Yes, exactly. So if you notice, if you have a nice childhood, if do you remember when you are a child, you can play like something like how you call it, very basic telephone. You use something like a cup and connect the cup using a string, and the string will carry the sound. That's basic principle. Basically, this the vibration of the atoms carry sound. That's why it's called phonon. But if we describe if we describe in quantum, we can study this oscillation in quantum physics. And this oscillation has some two types of oscillation. The first one is the acoustic phonon. Acoustic as the sound, so phonon that carry sound, and also there are phonon that carry optical phonon. So what is the difference? Difference is that in acoustic phonon, the nearby positive and negative electron moves in the same phase. However, in the optical phonon, they are moving in the different. So positive charge and negative charge seems like moving in different. Even though they are nearby, then moving in different phase. So it's like optical, because in optic you have electric field, and because of this electric field, the positive and negative moves differently. So it somehow looks like that, even though the k is the wave number is the same, and the movement is different because of the those type. So if you look carefully, the positive is the like black, and negative different, positive and negative, like different nearby atom, and this one is something like this. So they have some maximum energy, and there are some gap here, similar to the electron. There are similar to electron in solid, they have band gap, something like that, and also uh, phonon. So it's a little bit similar to photon but different. If photon is responsible for light, and phonon is responsible for sound in solid. Okay, now so remember, we describe electron using Fermi-Dirac statistic. But now you remember that there are one another kind of uh, quantum distribution, that is the Bose-Einstein statistic. So now we want to implement those Einstein. Why? Because in the Einstein solid, our discussion still is a semi-classical discussion. So the energy U is so the statistic here that they are used is still classical energy. However, we use the quantum energy. So now, if we want to understand fully, then we need to understand it as a as a more full quantum contribution. So now we should remember what is the Bose-Einstein. So Bose-Einstein statistic describe the movement of boson. So what is boson? Fermion is spin half, three half, five half, something like that. And boson describe the movement of spin integer particle, like zero and half and something like that. Okay. So yeah, as if you remember, I told you about something called quad or quantum state of the material, and some of it is called Bose-Einstein condensation. So let's move. Let's see at the animation. So this is the illustration. Yeah, so this state is called post-Einstein condensation because at the low energy, all become they all occupy the same energy, and this energy is observed. This phenomenon is observed as a post-Einstein condensation. Even though as a atom as a whole, it only occurs at low temperature, but in solid, it's this phenomena is observed in the phonon transport. So let's now focus more on the energy. If you can look at the energy, yeah. So as the let's focus on looking at the energy. So this illustrate the energy level, the quantum energy level that can be occupied by the atom, and each of this energy level have some probability that is governed by the Bose-Einstein distribution. So as when tau become zero, become smaller and smaller, those the probability here become very large, and we need to study it a little bit more carefully. So this distribution follow this distribution exponential beta e minus 1. So as this one become zero, that is become very large something. Okay. So in fact, this potential distribution is the one that is observed in black body radiation. So in black body radiation, if you remember again what you study in quantum mechanics, black body radiation is among one of the important phenomena that becomes the background of why people need to develop quantum physics. So if we only consider classical physics, the black body radiation should have this classical distribution. So as frequency become larger, the black body should give more uh, more radiation on this higher frequency. However, what is observed is that it it achieves some maximum, and as it after that maximum, the black body radiation becomes smaller and smaller for large frequency, and this can only be explained using this Bose-Einstein distribution, and it and the curve match the observed in experiment. So this is the actual trend that explain the real data, and this one is the classical approximation. So from this, using we now know that the Poisson distribution is actually occur and need to be considered if we study the statistic or phenomena uh, that involve the Bose-Einstein particle. So now back to the photon. Back to the phonon. So this collective phonon movement, now we will study it by taking some approximation here. So we will focus more on, as we saw that we want to study the heat transport. So basically we can focus only on the bottom one, uh, the acoustic phonon. So there are some the energy is approximately linear here. So we can assume that E or PC is P is the momentum, or P is spread by lambda, and also this C is not the light velocity. Yeah, for black-body radiation is light velocity, but here in solid, C is just is the velocity uh, of sound. Velocity of sound is the momentum of phonon, and there are some maximum. So we assume a maximum energy called d by is characterized by d by temperature, and also that this d by temperature is important. C as the sound velocity. So now the internal energy is described by this equation. So now if we want to study the internal energy, we can take uh, ratio of U, the internal energy, divided by the number of the oscillation, can be described by A. The top has some E and F. This is the Bose-Einstein distribution, and this the oscillation we only count the number of states here, something like this. Don't count the number of particles. We only want to know the number of oscillations, something like this. Okay, and we set a maximum momentum. Maximum momentum is just the maximum energy divided by C, something like this. So the number of the oscillation, if we have n particle, then the number of oscillation is just 3n. U divided by 3n, because it's three-dimensional particle. There are 3n. If just a chain, then just 1n. We have 3 dimensions, so 3n, and the above is something like this. The energy is P times C. This one is the Bose-Einstein distribution, and this one is P square P. The bottom is only this. So if we calculate this, we find that the internal energy is just 9 times n kBT 4 by TD 3. So if we make some substitution, we calculate this, and some substitution, we find this, and there are these terms, this integral, this x times x power 3 and divided by exponential x minus 1 dx. And this integration has some limit from 0 to t divided by t, and this is what's interesting here. So we can calculate this integral analytically or numerically, but we can study the like some limits, just to be more to understand a little bit more, but not going too deep to mathematical. So here, for example, for high temperature limit, do we can we regain the classical limit? So we can see here that now it's the same integral, but now for high temperature limit, that means the here become 3D divided by t. This t become really large. So for like 100 or 1000 or 10,000, you can find that here. And now it's become smaller, more than one, lots more than one. That's why in that case, yeah, because this x will be around from 0 and something less than 1, then small b is really small too. Because of that, we can take the limit, yeah, of this exponential x. If you remember exponential x, what is the Taylor expansion? It's 1 plus x plus something. 1 and 1, you can take out the 1, cancel each other, only x and higher terms remain. Yeah, for simplicity, we just take out these terms. So only x square, yeah, x square, and the integration of x square is just x3. So there are 3 td divided by 3 to the power of 3, and because of that, 4 and 3 is cancel each other. There are only 1. So the u depends on 3 and kBT. And now it's clearly, yeah, we can recover the classical energy that comes from the equipartition energy, 3 n kBT, number of particle n. So now the specific heat is just Cv divided n to T is 3 kB. So we exactly arrive at the classical limit. And this is what's nice about the quantum physics, that quantum physics at some limit it should arrive at the classical physics. In this case is Dulong-Petit law. So in this Debye model, so this overall is called Debye model. Debye model can describe the high temperature limit. So now can it describe the low temperature limit? Now let's see. So for low temperature limit, so what's changed? Because T becomes small, that means that this Debye divided by T tends to become infinite. It's become very large. You can assume just it's as a constant in the low temperature limit as infinite. So in this case, this integration 9 times something is just 3p. So this term is p power 4 divided by 15. So 9 divided by 15 is 3 over 5, something like this. So now we find that u is depends on 3 to the power of 4. From that, we know that the specific heat is Cv is 12 nkb T to the power of 3. So this is often called 3 device 3 cubic law, temperature cubic law, 3 cubic law, or just as simple as 3 cubic law. And this is what should be observed in solid. So here I took the figure from hyperphysics. So here if we write each of the graphic of each of the material of the solid, we find that this is PV, this red figure, this is AG, ALT. Yeah, we can characterize that using now the TD. TD now characterize each of the material. So TD from fitting we can find that is TD is 105 and AG is 225 and AL is 428 and diamond is something like this. So if we scale now every temperature not to Kelvin but to the Debye temperature, we now find that they all have similar value. And this is what's really interesting about quantum physics. So it's now we can now describe the heat specific really nicely, and it's really connected. So as a whole now, Debye model now can describe the heat specific of a solid correctly. So now we study as a conclusion of today's talk. We have described the specific heat of solid on the conduction electron also, and also from this lattice. And here we already saw that there are three model that is used: the Coulomb-Petit law, which is using classical equipartition theorem that find that only this is equal to 3k, and in instead solid it use some classical statistic plus quantum energy, and this describe this energy, the Einstein theory law, this one. And also there are there is Debye theory, which Debye model using quantum statistic, pure quantum statistic, and we can find that this distribution become something like this. So in the limits, they're essentially the same as Einstein. That in high temperature is 3k and low temperature is 0. However, the trend is the detailed trend match the exact uh, trend of the experiment of the of solid. So this is a very interesting phenomena. So you can show here that the transport phenomena at the solid obey the quantum statistic, and they have some can be modeled using quantum theory. So now we can back to the heat conductivity. So this specific heat is depend on in the low temperatures depends on 3T, 3 law, like this. And we find that this for silicon example here, that the low temperature behavior match the Debye model, and last is goes the Coulomb-Petit law. So again, we remember that the heat conductivity is connected to the Cv. Is connected to V square tau V and Cv. So now the Cv here obey this. However, in exact solid, this tau is not constant. So in some experiment, it's measured by I take it from this the data of the silicon, so that this the kappa exactly not. It is zero at low temperature, and also it's become small in the high temperature. So there are some peak here, and this come uh, the from some like deeper phenomena in solid state physics, that this tau is not really constant, but at high temperature it depends on the inverse of temperature. So the more, this is collision time. So the more temperature, the higher temperature, then the collision time becomes small and small. So at high temperature, the electron or the phonon or many things is tend to uh, have less collision time, because of it will tend to have more collision, because they are all moving very large and moving very extremely. So the probability of the scattering become more and more, and they become smaller. And so this CV now can be connected to the heat conductivity, and we show here that the kappa at low temperature is proportional. It has also the T cubic at T cubic law, so it's proportional to the T cubic here too. But in here, the this tau limit play important role and become smaller, something like that. And so now, yeah, that's the conclusion of today lecture. So today we studied about the heat conductivity, especially the heat specific, because the conductivity is connected to the heat specific, and the specific really is interesting. Many interesting physics hidden inside this theory. So this theory can be studied by simple classical approximation, but the more detailed should include the quantum energy and moreover the quantum statistic. And by appropriately studying them, then we know that we can describe the movement of the phonon and of the electron, and they can describe as a whole picture, describe the movement of the transport and heat conductivity and specific of the solid. So if you notice here that this is Cv is 3 to the power of 3. If you notice here that Pb, so if you it's in this part, so there is contribution of this is diamond aluminum and Ag and Pb here. So there are some, this three, the other three is nicely here, fit nicely here, as diamond is only until here, but the blue and green fit nicely. But there are some change, different between this Pb and Ag. Why is this? This is because we need for Pb is metal, and the other is mostly this diamond, for example, is a insulator. So in insulator, what comes uh, as an important is only the lattice vibration. So in insulator, you have lattice vibration, but you don't have constant electron as much. Because why? As you remember at the first lecture, I described that the electric transport quite different in in conductor and insulator is quite different, right? Because in conduction electron, in conductor, only the insulator, the electron doesn't move anywhere, and the conductor, electron move. So now, if we want to understand what's different between this, between red and blue, that comes from the heat capacity of the transport. So the the heat capacity of electron also must be considered, also contribute to the heat transport of conductor. So that's why here there are this little bit small change. It comes from the contribution of the electron. So to be exact, the at low temperature, the contribution of this not only come from the phonon, but also there are some contribution that comes from electron too. However, here we study like solid in general. So in general, phonon play important role, but for metal, we need to also to consider this the contribution of the free electron. This stuff. So yeah, in some materials, at low temperature, we can have uh, some kind of difference. So you know, okay. So yeah, as a conclusion, yeah, if we talk about metal, so the total contribution has contribution of the electron and phonon. So it has uh, T dependency to T and also dependency to T square. So this behavior is observed in metal. I think I don't have the slide yet. So yeah. Yeah, so in material, there's always some contribution to the from electron and phonon. Also, this only so far we only discussed about the electron and phonon. So in some other like more interesting materials, yeah, there are some hidden things that can contribute to the transport phenomena. For example, for ferromagnet or ferromagnetic materials, for example, their electron is not as simple as the metallic electron, because in ferromagnetic materials, electron the transport can depends on spin. There are spin up and spin down, something like that, and the spin can carry add to another degree of freedom, and this degree of freedom has different quantum distribution, and this quantum distribution can uh, generate like more interesting phenomena. And also this electron and phonon, for now we assume that they are independent to each other. However, in another interesting area, for example, in another interesting material, for example, superconductor. Yeah, superconductor, one of their origin of the superconductor is a strong correlation, strong interaction between electron and phonon. And in that case, these two cannot be treated different separately, and we need to consider their relative interaction and their like coupling together, and some strong correlation between them. And in that case, yeah, this temperature can be really become really interesting. So there are more in physics when we consider more interaction between many particles, and that's, I think, take home message that I want all to give you all, that in solid, yeah, many things can happen, and those things can be described to be by using like quantum physics, and also by some deeper physical law that govern this microscopic movement of the electron and any other quantum particle that describe the movement. Okay, do you have any question? Okay. So now we come to the end of this today's lecture. Do you have any question? So do you remember uh, about sorry, your pretest? Do you remember about your pretest? Hello. I think in the pretest, there are some question about which one is carried by electron. Is it heat, electric, or sound, or something else? I think. Yeah, I hope you now after hearing to this test, to hearing the lecture, I think you should be able to answer that. Okay, before we close this session, before we end our lecture, So I would like to thank you for your attention, and also yeah, let's take a picture together, I think, before we stop.
Doctor, can I ask a little bit?
Yeah, okay.
So about the CV, so in insulator,
Mhm.
the contribution of CV is only at the phonon, right? So electron,
Yes,
there is no contribution, right?
yes.
Or there is?
So yeah, in insulator, yes, it's only contribution only from T, because the electron now is bounded to uh, the electron only. So so here is okay. So, yeah, I missed something. So if you remember our like first lectures, there are some nice illustration here. So we need to remember, yeah, that when I talk about proton, and I separate proton and electron, what I mean is not only proton only, but nucleus, the valence, yeah, proton including the valence electron. So that's why in insulator, this, yeah, proton plus the valence electron is considered as a lattice together. They move together because they are tightly bound to the electron, to the proton. So I just consider. So I ignore this. I ignore this electron. Just assume like proton. So to be correct, the one that contributes is this valence electron plus the proton. The valence, the heat capacity of the valence electron, I ignore that discussion is beyond this lecture. So if you want to that's why in more advanced research, they don't consider only proton electron like in this lecture, but they also consider the valence electron, and those valence electron can be their dynamics can be a little bit more interesting, yeah, than just as simple as this one. This is a very simple picture that we assume that only there are photon only that is, and describe the photon, and also there are electrons that only condense electron, and we don't like this describe the valence part of the electron. Okay. But
Right,
yes,
Doctor.
yeah, that's why in the
Okay.
insulator, that in our discussion, the insulator only has the phonon, doesn't have the electron part. Why? Yeah, because insulator doesn't carry any electricity, but it still carry heat. That's why I told you sorry, this one, okay, the relation, the Wiedemann-Franz law. This is only for metal. In insulator, yeah, it's clear that uh, insulator has a sigma is zero. Yeah. For insulator, sigma is zero, and kappa is not zero. That's the different things. But this kappa, not the kappa of the electron, but kappa of the phonon. Yeah. So this contribution, this Wiedemann-Franz law only holds for metal. Why? Because in metal, electron can move freely, more freely than phonon. So this thermal conductivity of electron usually is more larger, more very large compared to the phonon in the metal. Why? Because in phonon, I think so yeah, that which ones? Yeah, this one. So because at some this temperature, for example, room temperature is around 300 something, right? So their kappa become like small because of this tau. The tau of phonon is quite different with tau of electron. Okay. Is there any other question? Okay. I hope you all enjoy. You all understand. So please don't hesitate to ask any question. Okay. Yeah, before we close this session, so please turn on your camera. I think I need to take some photo for the documentation of this program.
Yeah, Doctor.
Okay, hello others. Nurul, Gavin, Rehan, Aini, Saswan. Oh, there are some internal our there are student of our department too, not only from Malaysia. Okay, Aini. Okay, maybe she is online. Okay, just I will take picture in three. So please smile, everyone. One, two, three. Thank you. Okay. Let me check again. Wait a minute. Okay, nice. Yeah, thank you everyone for your attention. Okay, so don't forget uh, to write the to okay, don't remember don't forget to fill the attendance. Okay, I write it again. So please write the attendance, fill the attendance, and I hope you have you are now more interested in this like the series of in the capital selecta of selected topics of physics in this lecture. So I think there are more and more interesting physics that will be described by other lectures. So I hope you all enjoy your stay in Indonesia, and more importantly, you have some more understanding in physics and more interested in physics, and you can further pursue your career in physics. Okay, I think that's all for me today, and I hope to see you again in another chance inside this program or outside this program. Okay, thank you very much.
Yeah, thank you, Doctor.
Thank you, Doctor.
Terima kasih baik Pak.
Good morning to you all.